Hello, and welcome to today's webinar, How Inertial and GNSS Technology Enhances Autonomous Navigation with Autoware and RTMaps Ecosystems, brought to you by GPS World Magazine and our sponsor of the event, SBG Systems. Before we start, I want to let you know that today's webinar will be recorded. You are currently in a listen-only mode. A recording of this webinar will be posted to gpsworld.com/webinars and will also be emailed to you tomorrow. I'm Mackenzie Shoemaker, Content Marketing Producer for GPS World, and I will be the moderator for today's event. At this time, I'd like to acquaint you with the ways in which you can participate during today's presentation. Please notice the Q&A panel at the left-hand side of your console. If you have a question, type it into the panel's text box, then click Submit to place your question in queue. We encourage you to ask and enter any questions you may have for our speakers during the presentation. We will address these questions at the end of the presentation during the Q&A portion. Questions submitted during registration have already gone to our panelists and may be covered during the presentation. If you experience any technical difficulties during today's event, you may use the same Q&A panel on your screen to submit your issue, and assistant producer Joey Ciccolini or I will personally assist you. You may learn more about our speakers by viewing their bio, photo, and email address in the panel located on the upper left side of your console. To the right of your console, you will find a PDF of today's presentation slides, which you can download, and a link to visit both the SBG Systems website and the GPS World website. If you are logged into your social media accounts, you can share the webinar's title, description, and URL with your friends or colleagues using the Share This widget. Now, I'd like to introduce you to today's speakers. First, we will be hearing from Laurent Thuaut, business developer of Unmanned systems at SBG Systems. As a member of the senior staff, Laurent is tasked to align the company's strategy with the market trends to anticipate technological advances and to implement successful plans for growth in the sales channels. We will also be hearing from Armağan Arslan, co-founder and managing director for LeoDrive. During his management, LeoDrive has developed mobile mapping systems and autonomous vehicle localization solutions. And finally, we will be hearing from Nicolas, CEO of Intempora. Nicolas joined Intempora in 2001 and was appointed as CEO in June 2012. Since then, he has managed the company and continued to lead the technical team to edit software development and validation tools for customers all around the world. At this time, I'd like to pass the presentation over to you, Laurent. Go ahead and take it away.
Thank you. Thank you, Mackenzie. Hello, everyone, and welcome to this webinar that we've put together with two of our partners to present our solutions for autonomous vehicles. I hope you'll enjoy it. I am Laurent, business manager at SBG Systems with a focus on unmanned and autonomous applications. SBG Systems is a French manufacturer of inertial navigation devices, equipment that is used on board vehicles to position and navigate accurately anywhere, anytime. We are headquartered in France near Paris with a global presence serving customers worldwide. We've been active in the motion sensing industry for 14 years, and we have deployed more than 30,000 sensors in the field already. Today, almost all vehicles worldwide are positioned using global navigation satellite systems. This is the case for trains, vessels, public transport, planes, and of course, our cars. And these cars will need to know exactly where to position themselves within a lane at any time under all conditions. This is okay as long as we stay behind the wheel, but in the near future, we want to enable fully autonomous cars. And these cars will need to know exactly where to position themselves within a lane at any time under all conditions. However, you may have experienced yourself that under many conditions, we can lose GPS under tunnels, for example. you will be lost, but as you're driving, you can still position yourself in the right lane. Other situations in the so-called urban canyons are other examples of challenging environment to position with GNSS. To operate correctly, a receiver needs to track several satellites, and getting the only minimum 4 in view will not be enough to get an accurate and robust position. Using multiple constellations is a necessity, but will not be sufficient in most cases, like the one pictured here. How autonomous cars drive in this condition? That is the challenge that we are here to solve. So what is our solution then? INS is a combination of multi-sensor data into one device that is fusing GNSS, of course, but also inertial motion sensors measurements and other information such as odometry to provide an accurate position at any time. For our GNSS source, we are using all 4 constellations, which maximize signal availability in GNSS complex situations for autonomous navigation in urban canyon, like we've seen before. For precision, all our INS include RTK processing using either individual base stations or RTK network service and provide the expected centimeter level accuracy with immediate fixing thanks to the built-in multi-frequency receiver. To ensure performance and build trust, we assemble our own IMUs from carefully selected industrial-grade parts. Then we calibrate all our products individually. Units are placed in a thermal chamber on a multi-axis rotary table, cycling through the entire -40 degrees C to +85 temperature range. Yes, the calibration is applied over the entire temperature range and in the 3 axes of motion, plus a dedicated calibration report is made available to the customer. We've made serious investments in the process and cutting-edge technology to guarantee IMU performance and stability over time and across samples. In addition to that, rigorous sensor selection associated with carefully crafted signal processing is our recipe to compensate for shock and vibration. More than just performant and accurate devices, we need integrity in positioning to deliver a trusted and reliable navigation for self-driving. Most applications have a maximum error budget and their requirement that we call the alert limit. It's then critical for a navigation system to report an estimated error that matches the reality to avoid misleading operations. In the following diagrams, we show top left a reported error that is lower than the actual error and the predefined alert limit. The system is then safe to operate. Next right is a situation where the reported error beyond the alert limit is no longer acceptable. Real position error is still lower than the reported one, and the system is safely declared as unavailable. Bottom left, the reported error is lower than the actual error. The situation starts to be dangerous, although real error is lower than user requirements. And finally, bottom right, the situation is critical and misleading as the solution is declared unavailable, but the real error is above user limits. Those last 2 scenarios are the one we never want to see. The integrity should be addressed at every step of the navigation chain, starting from the correction service used and ending at the navigation sensor side. In our case, on the receiver part, we achieve integrity implementing advanced RAIN, which is composed of a fault detection and exclusion algorithm and the computation of protection levels. To assess integrity, we are commonly referring to the Stanford diagram. Looking at the 2 cases to be avoided as seen previously, misleading information and represented by events situated below the diagonal of the diagram where position error exceeds the protection levels. Critical misleading information are contained in the area where events are also greater than the alert limit, that is the red square here. Consequently, safe operations are represented by the white triangle area, and the yellow part depicts situation where the solution is declared unavailable. Let's conclude here looking at some experiments conducted in real-life environment, consisting of an automotive test scenario in a deep urban area located in the business district of La Défense, west of Paris. We have here the SBG System test vehicle equipped with two devices under test: a GNSS-only automotive-grade multiband RTK receiver equipped with our FDE and protection level determination algorithm. Second, an industrial-grade MEMS INS produced by SBG System, which is an RTK tightly coupled IMU with odometry input. As for the reference system, we've been using a high-quality fog-based INS with odometer and subsequently post-processed kinematic. Then we've compared the result obtained in GNSS only versus tight coupled solution. On top, the GNSS only measurements are all scattered in the upper diagonal part of the graph with outliers of few hundred meters going well above the alert limit, still contained with the calculated protection levels. That solution is indeed not suited for self-driving. Thanks to the FD algorithm and correctly detects and excludes the faulty measurements, our integrity algorithm provides a reliable protection level that bounds the position error without any misleading information reported in both GNSS only and tightly coupled INS. Under deep environment, tightly coupled multi-sensor fusion GNSS, INS, and odometer improve significantly the solution availability, accuracy, and protection levels, especially during the partial or full GNSS outages. However, this solution alone, if delivering reliable positioning, isn't accurate enough to satisfy self-driving in most severe conditions. That is why it is necessary to complement the solution with the integration of supplementary sensors such as cameras or LiDARs. Integrating all these instrumentation to satisfy the perception stack of an autonomous vehicle can be a complicated task, considering that you have a number of multiple sensors to put together: LiDAR, radars, and cameras. Then it comes a time to have them connected, and most importantly, to have them precisely time synchronized to create an accurate view of the environment, using PPS and MEA-ZDA over various interfaces such as serial or the CAN bus, for example. Cabling will quickly turn out to be a complex and rapidly will face the nightmare known as the spaghetti cabling syndrome. Time synchronization is, however, critical in systems that involve multiple components in autonomous vehicle, and setup must be carefully undertaken. Besides these legacy interfaces at SBG Systems, we have also implemented UDP protocols for the time synchronization over Ethernet of our INS and other connected device on board. That will drastically ease the integration of the vehicles with pre-installed Ethernet networks. For time synchronization, we are offering the alternatives of both NTP and PTP time servers. PTP, if selected, is the most precise of the two. It is offering time resolution better than 100 nanoseconds. Our PTP solution is IEEE 1588 compliant and will seamlessly integrate in an all PTP-ready system. And for sure, all of that is integrated into the INS component. That most importantly means no longer you shall need dedicated and separate Grandmaster clock hardware, as the INS itself will serve that purpose. That is a more economical overall solution. Less equipment means and less space scaling and reduced complexity, leading to a more efficient sensor synchronization system overall for autonomous vehicle. Next to this, we have implemented an entry client to simplify the reception of positional corrections with our Ethernet-ready INS/GNSS product. This feature will give the option to easily retrieve RTK corrections in area where a subscription of this type of correction is available. Extra complexity in designing your system will likewise be reduced in this case as well. For mobility, we serve many segments on-road and off-road. First, we do supply survey-grade hardware and software to support the activities of HD mapping. We have customers integrating autonomous shuttles, but also last-mile delivery robots. We are active in the early stages of urban air mobility development, supplying to several actors in that segment. For sure, we do address the issues encountered for driverless cars, as previously explained. Finally, autonomous trucking is an extremely interesting application for us, where we already support advanced developments behind the proof of concept. Now I will show how we specifically address the different activities in autonomous vehicles. They are categorized in 3 different areas: HD maps, real-time localization, and then assessing the performance of your system. For HD mapping, SBG Systems offers high-end survey-grade solution that can directly georeference the object and images very accurately, previously acquired by a LiDAR or camera. On the real-time localization range, we will be looking at more compact systems, somewhat less precise but more affordable for volume production. Lastly, for your performance assessment, we propose a post-processing software that we have designed in-house with the aforementioned tightly coupled algorithm. To terminate my part of the presentation, I will quickly introduce now a few of our products that are relevant for autonomous operation. First, NavSight, which is a survey INS equipment delivering better than 0.005 roll pitch and better than 0.01 degree heading with centimeter level processing. The Ellipse series will be suitable for real-time navigation with performance as good as 0.05 degree and 0.2 degree heading, and centimeter level positioning with RTK single or dual GNSS antennas. And finally, this is our PPK post-processing software, Inertia. Additionally, to be useful for HD mapping operation, this software is typically used by our customers to replay offline after the mission the navigation of the vehicle in order to determine where they need to correct their own algorithm in terms of positioning and orientation. The software can access more than 8,000 base stations worldwide for sourcing positional corrections. It implements forward, backward, and merge processing. It is open to support third-party GNSS and IMUs, and not only the SBGs. It is also possible to acquire a time-based license of Inertia for the time being of all your setups, including lever arms calibration, for example. We offer scalable and cost-effective pricing model for power users and integrators. Our solution comes ready for easy integration with accessories such as antennas, software components for configuration monitoring and analysis, ROS, ROS2, and RTMaps drivers that will ensure a seamless integration in the dedicated autonomous vehicle ecosystem. That will be introduced by the next 2 presenters. I hope you enjoy this part of the webinar, and it's now up to Armağan to relate his experience integrating SBG system component into the Ottaware ecosystem. Now, Armağan, the floor is yours.
Hello, Laurent. Hello, everyone. Thanks for today's presentation, and thanks for all the explanation about SBG Systems and the products. And I want to start with LeoDrive's part of the presentation. So today I will talk about our company as low as possible, not to take your time. And LeoDrive is a partner, a premium partner of Ottaware. Ottaware is a foundation where we develop open source autonomous driving software, and we highly encourage everyone to contribute or just to be part of it. And I will talk about the applications that we made so far and that we are planning to make in Autoware. And then we will talk about the usage of SBG Systems hardware and software for HD mapping and localization in Autoware Auto and ROS 2 parts. This part will be presented by our tech lead, Fatih, and he will take over these parts from me when the slides arrive. So I want to start with our team. First of all, I'm Managing Director of LeoDrive, and we are focused in the development of full-stack autonomous solutions, and we are also working with other type of unmanned vehicles as well. Our core business is autonomous driving platform development for different type of vehicles, autonomy kit sales, I will show an example of it, and sensor and system integration for OEMs. We have two products to sell. One is Torch. It's an indoor 3D mobile scanner, and we have a product called Navi, which is a autonomy kit for AV researchers or the starters who wants to test their algorithms. Our team is 18 right now, and we are based in Istanbul, Turkey. I want to talk about the steps that we are taking to develop an autonomous vehicle. At least on our side, this is how the process goes. So what we do is we engage with the vehicle and try to understand its dynamics and try to understand how it will behave in a simulation environment. We make the sensor placement and create a operational design domain, which also serves us for the simulation environment. After the first analysis, we move on to design and integration part. At this part, we design sensor housings and try to create the electrical design as well and the interfacing of them to the computer system selected. So after the integration part is done, we start with sensor calibration, time synchronization, and data collection to develop our algorithms. And these collected data, sorry for that, can be used for both developing the 3D perception stack, which consists of cameras and LiDARs mostly, and detection, tracking, and prediction of the environmental obstacles and other agents around us. And also the INS and LiDAR data serves us to create the 3D map, which will be used in Localization Stack and also which will be used to create the HD map. And since we will talk about it more on mapping and localization, I will move on to path planning. After the HD map is created and the localization stack works fine, then we know where our vehicle, we can understand what's around us, then we move on with path planning. And in this image example here, we are seeing a vehicle trying to drive in the given direction, and also it's trying to change lanes if there is an obstacle. And with the path planning inputs, we are trying to control the vehicle in lateral and longitudinal so that the actuators are doing the necessary actions like braking, steering, and throttle. To be able to use this vehicle, we are creating a user interface. And in this user interface, we have some mode switching functions for different type of driving, some diagnostic screens for the test driver to check, and also to drive the vehicle, there is a mission planning screen. So this is how we operate. In this slide, I want to gather some information about what we have done so far. We have completed 3 projects until now. As a startup, this is a big thing for us. The first project was a ADAS research vehicle where we put around something like 40 sensors along with computers and other systems to be able to collect data and some of the test some of the ADAS functions like lane keep assist and autonomous emergency braking. And after that, we have started our project with a military company in Turkey to develop an unmanned armored military vehicle, which is completed. And this vehicle was the first example that we put on the environment so far with ROS and Autoware AI support, and of course further developed with respect to the needs of the military. But it was the first example that we made. And after the things that we learned from that vehicle, we move on to autonomous electric bus, which is currently running with ROS2 and Ottaware.auto, which is the current version of Ottaware developed and maintained. As I said, we have 2 shippable products. One is indoor mapping system. It is basically used for volume calculation and area measurement in GPS-denied environments. In this product, we are using Ellipse A Micro HRS. It's 10 grams and you can fit it well under the LiDAR and next to the camera so that we have straight maps with roll pitch compensation. And in this other kit, we are using LiDARs and cameras along with GPS-INS where people can map the environment and also use it as a perception system and also for a localization system. So in this vehicle, we are using 2 antennas on the back so that the antennas are not affected from the LiDARs and other interference, and we have dual antenna heading at all times. We have worked with Turkish companies until now, and these companies are most well known in Turkey, and we have other industrial customers as well in the field, also out of the field like aerospace, where we work together to understand the requirements. So I want to talk more about what can be done using Ottaware. As I said, anyone can use it, and we are always open to collaboration. And there are basically 4 application areas that we see possible today using Autoware Auto, and the first one is Autonomy Exploration. For the companies who wants to test autonomous functionality in their vehicles, or who wants to start with development, autonomy could be challenging by means of sensor integration, calibration, time synchronization, and also knowing the lever arms and how to get the best data out of it. So we created the systems which we think that could be tested and used with Autoware.auto. Also, currently we are working on an ODD called Cargo Delivery ODD, which we think could be used for both autonomous delivery and autonomous logistics. And in Autoware AI and ROS, we were testing autonomous people movers already, but currently this is a plan to create an autonomous people mover using Autoware.auto. So these all applications are mostly possible today and will be possible in the next couple of months. So I want to talk a little bit about the SBG Systems usage and advantages that we had in the past. So this is on the right. This was the first prototype of our mapping system. which consists of ellipse D unit and a Velodyne LiDAR. So in this setup, we have used SBG and its documentation made it so easier for us to integrate, and the ROS and ROS2 driver is very well maintained, and they are up to date, and you can ask any question. The support is so good on that side as well. And we are able to use also the IMU output, the raw IMU data in it, to merge with other localization algorithms. And after collection of the data, there is a easy to use and I think a low budget software called Inertia for especially ellipse products, where we are using it to create georeference point cloud maps to be used for localization. So with having said that, I want to give the word to Fatih, our tech lead, who will describe in detail of the technical usage of it. Fatih?
Hello, I'm Fatih. Here I want to explain what kind of data is being output from the SBG Inertia software. So we use the SBG Systems Ellipse D product to create maps and aid in the real-time localization of the vehicle. In order to create the maps, we first record some data using the LiDAR and the GNSS. We then give the SBG data to the logged binary data to the Inertia software, and this Inertia software post-processes this data using the RTK and PPK and gives us the refined path of the sensor. I want to go over some of the data that is being output from the Inertia software. So these are the UTC time and date and the timestamp. So these timestamps are given with the microsecond accuracy, and also the GPS timestamp gives us the perfect time, and also it gives us the rotation of the INS sensor in the world, and this is giving us in two ways. One of them is for variable quaternion data, and the other one is the roll pitch representation. The both gives us the same rotation information, but the roll pitch has the gimbal lock, so we don't use that most of the time. And it gives us the errors of these values. So also the latitude and longitude is given too, and we use the local Cartesian coordinate transformations to get our local coordinates. And we use these errors to get rid of the data where the accuracy is low, and we compensate those parts using the SLAM. Let's go to the next slide. So here I want to explain how we do the mapping using the data output from the Inertia. So first, we have two stored data. One of them is the GNSS-INS data that we have seen before, and the other one is the LiDAR data. We record this from a VLS 128, and it's stored as a PCAP file, and it's synchronized with the GNSS-INS using the PPS and GPRMC messages and signals. The PPS stands for the pulse per second. Every second it sends out an electrical pulse. And the GPRMC message contains the current time and date to the LiDAR. And LiDAR marks each single individual point with a timestamp, so we are able to create a very, very accurate map. And we have the microsecond accuracy to perform this synchronization. So here is the VLS 128, and underneath we have the IMU placed, the GNSS INS, and we have these two back antennas with 1.6 meter distance between them, providing us with the about 0.02 degrees accuracy, and even lower with the inertia post-processing. And then using this post-process data and the LiDAR raw data, we convert them to the usable timestamped points and the LiDAR local Cartesian IMU transformations, and then using the transformation between the LiDAR and the IMU, we start generating the map. So normally we just transform each point to the IMU's coordinate space and then create the map. But sometimes in between the buildings or some the GPS denied environments, it's not possible to generate the map just using the GNSS. Here we use the aid from the SLAM algorithms. So for that, we gather around the points to point clouds, and then we use the GNSS data too, and then we do the LiDAR distortion correction because the LiDAR is a rotating sensor and it creates some distortions. And then using these timestamp point clouds and the GNSS prior information, we put them into the SLAM, and SLAM works best in the GNSS denied environments mostly because we have very structured buildings and some other features that we can hang on. And we get the transformations from the SLAM algorithm too. And then the map generator uses these informations to generate the map. And then also, in order to get rid of some moving obstacles or transient obstacles, such as vehicles, we use the perception module to do some object detection, and then we remove them from the map. And then in the end, we have this georeference point cloud map to be used in the localization stack. And in the localization stack, I want to go over the localization stack that is currently being used in the Ottaware Auto. And Autoware Auto uses ROS 2. And then first, we have the point cloud map. And in the point cloud map, we have the points, and they are all georeferenced. And then for the localization, first, we have a point cloud map loader. This gets the map stored in the local drive and then publishes it to the NDT matcher node. The NDT stands for Normal Distribution Transform, and it is used to locate a point cloud. Like we have these green points here. These are the live points coming from a LiDAR, and the NDT algorithm tries to locate where this point cloud is located within the map. So it could be anywhere in the map, these points, but it does some feature extraction and matching, and it finds where the vehicle is. In order to do this, we give it some prior information. So we give it the GNSS data, for example, and it serves as a prior information, and this is being used to initialize the NDT matcher. And this NDT matcher requires the real-time point cloud too. So for this, we have multiple LiDARs on the vehicle. We combine them into a single point cloud and then downsample it in order to make it easier for NDT to process, because the point clouds can be so dense and large. And using these downsampled points, the NDT matcher finds the exact location of the vehicle. And also, this GNSS INS driver gives us some information about where the vehicle is, but sometimes in the GNSS denied environments, this might not be correct. So the NDT matches transformation output and the GNSS INS drivers output, they both go into the EKF state estimator. And this node incorporates both information coming from the NDT and the GNSS driver, and it gives us the best possible location of the vehicle on the map. And then this location information, the transformation information, is used by the other nodes to perform the other algorithms and make the self-driving possible. That's it from me. Thanks.
Thank you, Fatih. And this concludes our part. Nicolas, if you are ready, we can give it to you, the presentation. We don't hear you right now if you're talking.
Nicolas, are you there?
Hello, can you hear me?
Yes, we can hear you now.
Okay, I switched the audio source. So my name is, sorry for the glitch. My name is Nicolas Dulac. I am CEO with Intempora. At Intempora, we are software editors. And we have over 20 years of expertise in software development for multi-sensor real-time systems. We mainly develop a software called RTMaps, which stands for Real-Time Multi-Sensor Applications. And we've been working with SBG sensors and interfacing SBG sensors since many years. Also note that since a little more than 1 year, we have joined the DSpace group. We are now a company from DSpace. We address different domains such as autonomous driving, development and testing of autonomous driving systems, advanced driving assistance systems, but also mobile robotics and complex systems such as complex instrumentation, 3D mapping, human factors and ergonomics, drones, complex advanced HMIs. So the common factor between all these applications is a requirement to make use, to process, to acquire, to process, to manipulate multiple data streams from multiple sensors in parallel. A short RTMaps presentation. RTMaps is really, as I mentioned, it stands for real-time multi-sensor application, not real-time maps. The name is quite misleading. It's a development, design, and execution environment for multiple data streams applications, proposing a component-based approach. So based on available components, you can acquire data from different sources. So here we should have a video, right? Is the video on here? Yeah, I think so. So here you can see on the graph that you can drag and drop components, connect them together with connections, so establish the different data flows, and the data streams from the multiple sources will execute in parallel and will be processed in parallel in multi-core and multi-CPU architectures. RTMaps comes with an easy-to-use development environment. It's really made for automotive engineers, mobile robotics engineers, and not software specialists. So thanks to the graphical design environment, it comes with a comprehensive library of off-the-shelf components and interoperability components with multiple other tools such as MATLAB and Simulink and ROS and OpenCV, TensorFlow, and so on. And it's really made for optimized execution in real time. It also proposes capabilities for data recording the different data streams from different sensors that are captured, and being able to play them back in a correlated way to simulate the presence of the real sensors and work offline. So next slide is a short presentation, a video of how it is look like, accelerated video, where you can see in accelerated mode components being instantiated, connected together, the execution starting right away when launching the data streams. And you can manipulate, you can work with camera data, multi-cameras, multi-lidars, radars, positioning systems, etc. without writing code. You can, of course, design your own components and write your own components, integrate your own features in C++ or in Python, or even in the form of Simulink models that you would, from which you would generate code directly into in the form of RTMaps component compiled. In terms of use cases, several use cases can be addressed with RTMaps. Simple applications such as data collection, which just consists in capturing data from multiple sensors. And this can be done on different kind of platforms, lightweight platforms, industrial PCs, or high-performance data recorders. Here, the Ottaware system from Displays with up to 50 gigabits per second and 32 terabytes of built-in storage. RTMaps can be used to run and execute the real-time software for autonomous driving vehicles of different kinds and robots. So in real time, capturing the data, running the processes, fusing the data, positioning the vehicle, and running the different algorithms and performing the command control. It can also be used on other kinds of complex systems with multiple sensors. When it comes to using SBG systems, SBG positioning system sensors are systems that we interface since many years and that are used by a number of common customers. Typically, you end up in RTMaps with a specific package called RTMaps SBG Systems of PCK with two components, one for capturing the raw data from the sensor and another for potentially splitting the different signals into usable different categories of information that you can use downstream in your application. So typically connecting to an SBG system and start using it is a matter of a few tens of seconds and a few drag and drop operations. In terms of execution performance, with RTMaps we focus on ease of use and execution performance. Note that RTMaps does not introduce hardly any CPU overhead. It's based on single process execution, multi-thread execution with intra-process memory sharing. So components just exchange pointers asynchronously. So there is no memory copies, no dynamic memory allocation during execution, based on pre-allocated buffers. So that means RTMaps will really take the most out of your computing infrastructure and will use the computing capabilities just to run the algorithms and not the middleware itself, which is not the case for other architectures, and performing benchmarks at the different configurations for data capture and data logging with high bandwidth sensors like HD cams. You can measure that the difference in terms of processing consumption, CPU consumption, is significant, up to a point where with different design, it becomes difficult to keep all the data, and data is missed. So we have, as I mentioned, a number of common customers with SBG who use RTMaps as middleware and, among other things, SBG sensors in their complex applications. So for the localization part, based on a combined approach with GPS, IMU, and potentially LiDAR SLAM, visual SLAM, etc., in order to have accurate and reliable positioning everywhere in any conditions. This is one of them, of this customer, Coast Autonomous. They are building level 5 autonomous shuttles in the US, and typically Pierre states that RTMaps and SBG Systems are able to allow them to efficiently design reliable and optimized localization and navigation algorithms for their autonomous shuttle development activities. Here, different other use cases from another customer. Here, the CEA list. These guys are doing, they did autonomous parking for big buses, public transport buses. So the bus was very large into indoor environments, and the bus was able to park itself with a few centimeters accuracy in between two other buses, hence saving room and time for the drivers, using SBG systems for positioning along with LiDAR SLAM. Here, something also a positioning application where soldiers were equipped with indoor localization systems based on SBG IMUs and visual SLAM, and they were able to navigate indoor into tunnels and buildings, several floors, in complete autonomy with a backpack, a lightweight system, integrating 2 stereo cameras and 1 SBG sensor. These are a few of the main customers. Several of them, which I didn't mention, use also SBG sensors in their more complex application, along with other sensors. We can figure out a number of car manufacturers, OEMs, tier ones, universities, engineering companies, and also some names in the defense area and other domains. So that was my presentation. I'll be happy to answer any question after this. Thank you, Mackenzie, for this opportunity, and I hand over to you for concluding the webinar.
Thank you all. That was great. All right. At this time, we are going to jump into our Q&A. The first one I have is for Laurent. What kind of license do you offer for Inertia? Only annual subscription or monthly?
Do you hear me now, Mackenzie?
I'm sorry, what?
Yeah. For Inertia Software, we offer both time-based temporary license that you can get by the month or by the year, as well as offering a perpetual license that you can get for the software itself. Very specifically for power user integrator, we also have pay-as-you-go type of payment that we authorize for the usage of the software for integrator.
Great. All right, my next question is for Nicolas. How is it possible to develop our own RTMaps components in order to integrate our own functions based on SBG sensor measurements and other sensors, for instance?
Right, thank you. Yeah, typically you can develop your own building blocks to integrate graphically in the RTMap Studio in your applications and connect with your different sensors, including SBG, of course. And you can do that with the C++ API or also Python API to develop higher level functions and faster. And the third way, more and more appreciated, mainly for command control applications as well, is to develop these components in the form of Simulink models and generate code with the Simulink encoder directly into the form of RTMaps components that can be executable.
Great. All right, my next question is for Armağan. Does Ottaware have a localization structure ready to be used, and is it open for everyone to use?
Thank you for the question. Autoware has localization algorithms already operational in both ROS and ROS2. It's open for everyone to use, that's correct, but we also highly encourage and recommend people to get into the development. If they have anything they want to test, like visual localization algorithm, we highly encourage people to join our foundation. Thank you.
Great. All right, my next question is for Laurent. Someone said, my application is real-time only. Is there an advantage of using Inertia in this case?
Yeah, thank you for the question, Mackenzie. When you have a real-time application, yeah, Inertia can still be of interest for a user. And in that case, imagine that he's developing his own algorithm for navigation. Inertia will be here to help assess the performance of the system by replaying offline the navigation. So that is the case that will help. In that case, yeah, you will, for assessment of performance, Inertia will be useful in real-time operations.
Great, thank you. We have time for one more question, and this one is for Nicolas. Onto which kind of OS and platforms is RTMaps available?
Oh, thank you. Yeah, indeed, RTMaps can be used on a number of OSs and platforms. It's available in a standard manner on Windows and Linux, on different architectures, typically a PC, so you can very easily prototype your applications on a PC. We also support a number of embedded platforms such as NVIDIA, Jetson, and Drive series, Raspberry Pi, or a number of other ARM-based platforms, Renaissance and XP. And in terms of OS, we can also, of course, target real-time OS such as QNX for really deterministic execution of the applications, of the software.
Great, thank you. Thank you all for sharing these insights with us today. We are going to wrap up now. Thank you so much for attending today's webinar, How Inertial GNSS Technology Enhances Autonomous Navigation with Autoware and RTMaps Ecosystems, brought to you by GPS World Magazine and our sponsor of the event, SBG Systems. If you have any additional questions for myself or for our speakers, you can reach out to us directly via the email addresses you see on the screen. A PDF of today's presentation will be emailed to you following the presentation, and a recording of this webinar will also be emailed to you and posted to gpsworld.com/webinars. Upcoming webinars from GPS World will also be posted to that page. Thank you all for attending, and we hope you'll come to another great webinar.